Hi everyone, and welcome back to a new video about system identification, and this is example number 6. In this example I will discuss a new sort of a system, which is a pure integrator. And again we will look at the calculation step by step, and we will verify this using MATLAB simulations. So let's look at our example. What we have is the following situation. We have the step response of a system, and the input R is given here in red, which is a step input, has an amplitude of 3. You can already see that it has a value of 3, and it starts at 0 and it will stay 3 forever starting from 0. Now we would like to determine the transfer function using this plot. What we have is, of course, not only the input, but we have the response, which is given in blue, and that is different than the previous examples. We had also the step input, but the response was actually a curve which will settle at some final value. In this case we have a curve, or we have a line actually, which is still increasing without a bound. So we will like to determine then what is then the transfer function for this case, and that is actually what we call a pure integrator. So the solution step by step, let's look at the observation from the plot. And of course the output is the most important part here. So first with the output, we can see that it is linearly increasing without a limit. So there is no final value actually here. That is, as already said, a typical pure integrator response. So this is definitely a pure integrator. What we also see here in the response is that we can define or determine from the plot a point that we can use later on for determination of the transfer function of our integrator. Now if I look at my plot and I see at 10 seconds, because the x-axis is given in seconds, I have a value of 4 for my blue line. Of course I can take another value, it doesn't matter for the calculation, you will get still the same transfer function, but I just took this and that will do job. So I have the following. You can see then that the slope of this blue line is 4/10. So you go up 4 if you go 10 in the x direction, plus x direction. So you have then 0.4 as your slope. Okay, that will be used later on. So what's then actually the transfer function model for this pure integrator? Now for a pure integrator, without any zero or any delay, the following transfer function can be used. There are of course different representations of this one. You can see we have two unknowns, or two parameters, the ki and the tau I. Ki here is the integrator gain at a particular time, t1, so that is actually what you really need to choose yourself in this plot. The tau I, which is the integrator time constant, is also at that particular time t1. So if you took a t1 for your gain, that t1 must be also used for determining the integrator time constant. This will be clear shortly when we determine the actual transfer function of this system. So let's move on to the transfer function of our system. First, the integrator gain. As I said, we need to choose something as a particular time where we determine the ki and the tau I. So I have just taken the 10 seconds I have already determined here in my first analysis. So I have t1 as 10 seconds. Then I can say what is then the gain. The gain is actually the value of your output divided by the value of your input. Now in this case I have determined that as y at that t1, which is 10, divided by the input r evaluated at 10 seconds. Now if I look at my value of the blue line, which is output, it will be at 10, 4, so it is then 4 in the numerator for the output, and the input is always 3 no matter what you choose for your t. So we have then also the value of 3 there, so that will be 3. So you will have 4/3 as your ki. That will be the integrator gain. Now the time constant, tau I, is just that value what you have chosen for t1. Again, if you choose, for example, for t1 5, maybe here, that will you will get this value, and that will be maybe 2 or maybe less, maybe a little bit larger you cannot see that clearly from here, but that will be of course used then here, and you will get exactly the same transfer function. Of course the ki and the tau I will be different. Okay, let's then continue with this one. Using these two parameters, we can then have the following ratio of ki over tau I, which is then 4 over 3 over 10, that will be 2 over 15. And that is actually the important part, because this will not change. The ratio of ki over tau I will not change, no matter what kind of value you take for the tau for t1, so which is the particular time in this plot. So alternatively, of course, if you don't like this method or you prefer another method, you can also say, okay, I will just look at the ki over tau I, which is just the slope, because that's always constant. That doesn't change. Whatever you take actually as the point here, that is actually the output slope. So it is the slope of your output, your response, divided by the input of your step. So that is actually, I mean, the amplitude of your step input. So if I get these values, so the output slope, which is 0.4, and the input amplitude, the step input amplitude was 3, then I will get exactly 2 over 15. So it's exactly the same as this one. And this will be, of course, shorter. I've done this, of course, to show you that you also have a different form or different way to determine that transfer function. So that is an alternative. Then we have the following situation. Just substitute the values for ki over tau I. In this expression, you will have then 4 over 3 over 10s. That's what you get. And if you simplify this, you will have 2 over 15s. And that's actually the transfer function we required to have in this example. Then, if you say, I want to have an alternative calculation for the complete analysis, then you can use Laplace transform directly. What is then the Laplace transform in this case for, and how do we use that directly? Now, what you do is, we have of course a couple of steps. First, determine the Laplace transform of your input signal, which is of course the R, so this is in time domain, and we need to go to the Laplace domain, S domain. That is actually the Laplace transform of your input, which is given by this. The second step is the determination of the Laplace transform of the output signal, which is Y, and that is then again the Laplace transform of your time representation of your output signal. And these two signals we need to determine mathematically as a time function. And then using those R and the Y, we can have the H, which is then Y over R, which is then just a transfer function. And that will give the exact same transfer function as we have here. So let's then look at the time representation of the input and output. The input R is a unit step, so it is a U, but it has an amplitude of 3. So that is actually what we need, 3 here in front of this one. That's actually just what it is for the time representation of your input signal. For your output, we know it has a slope of a 0.4, so it is a linear function. It starts at 0.0, so that's actually the origin. So we can say, for as a general formula, at plus b, so which is a is the slope of the function and the b is the beginning value, we can see that the b will be 0 here, so it will be 0.4t. So that will be this function, just a mathematical expression. What we then do next step is, as we see here also in the steps, we just determine the the Laplace transform of the input and also the Laplace transform of the output. So first, the Laplace transform of the input, that will be 3 over s. That will be that you can use this, or you can find this from the Laplace transform table, because the Laplace transform of a unit step input is 1 over s, and if you do that 3 times, you will get 3 over s. That's actually the very straightforward analysis. And if you go to the Laplace transform for the output, and for this t, for example, you will get 1 over s squared, but since there's a 0.4 here, you will get 0.4 over s squared. So it's actually just the amplitude, which is not 1 but 0.4. Now if you combine these, because we know that we require to have the r and the y, so this is the r, capital RS, and that's the capital YS, and we can then use this formula and then calculate the h. That is then 0.4 over s squared over 3 over s. and that will be simplified again this expression. So you can see just directly using Laplace transform you also get this. Which of course really need to have is the time representation or the function of this output and also the input in time domain that will give you the Laplace transform of your transfer function directly. So that is actually what you prefer. So I have just shown you another way to determine the Laplace transform. So let's look at the simulation results to verify this, and then we will see what we have. So let's jump to the simulations. So first we will begin with the transfer response, and in particular the step response. That is actually what we have from a step response. In this case the step input is 3. That's why we have for the system RH, that R is actually the input of 3 and H is actually the actual system. What you see is I have just given two labels. So the first, and this is actually our transfer function. You can see the first one, which is at time 10, it was 4, so it is actually correct. I have of course again determined another point, just gave as a extra check. You can see at time 5, which is just 2 times less in this time, I will have a value of 2. So you can see that this is really a linear function. You can of course take another value and you will then check for yourself what it will be. You can also look at 15 and it will be 6 because you go up by 2 for each increase in the time of 5 seconds. And that is actually a verification of that this transfer function is correct, just looking at the step response. Of course, let's also look at it in the Bode plot and then verify this even carefully. This is the Bode diagram. Again, I have labeled some values here. You can see this is again the transfer function, but I have rewritten this in a little bit different form. 2 over 15s, that's actually what we have originally, but I have then now 1 over a value times s. And this value is what's also called the time constant of the integrator, of the total integrator. So this is the pure integrator formula, and 1 over that tau s, and this tau is what we really need to, or what we can use to determine or check our Bode diagram. Now this value here is a nice check to determine that this function is correct. You can see that the magnitude here is approximately 0. It was impossible for me to get it exactly at 0, but this is really close to 0. It's very small. You can see the frequency here is 0.133. And how can we determine this frequency, and where do you see that in our transfer function? Now, you can also see that the phase is at that same frequency as minus 90 degrees, and actually the phase will stay at minus 90 degrees. Why? Because this function will always have a phase shift of minus 90 degrees, no matter what the frequency will be. But let's look at this frequency of 0.133 carefully. So why is this? And again, you can also see this value here. And what you see is that the magnitude here is 20 dB and here approximately 0. So you will go down by 20 dB. If you increase your frequency from 0.0133 to 0.133. So it is actually increase of your frequency of 10 times. So it is a 1 decade increase in your frequency, and you will go down by 20 dB. And that's actually a particular characteristic of a first order integrator, pure integrator. So that's actually another check that this is indeed the correct solution, but we'll still need to check that this frequency, because that is actually important. Now, again, the phase is still minus 90 degrees. That will not change, and that was independent of the frequency. If I rewrite this in j omega domain, which is just the stationary value for your omega, again, I just substitute for that the s is equal to j omega. That is only what you do. Then you can see that this is rewritten in a different form. This is the formula, general formula model that you can use to determine the tau. In this case, the tau is then 15 over 2. So the tau is 15 over 2 seconds, which is then 7.5 seconds. Then this frequency, which you see here, 0.133, will give you a magnitude of 0 dB, which is actually as a scalar 1. That means you have a gain of 1 at this frequency. This is also called the unity gain frequency, because it has a gain of 1 unity at that frequency. And for that, you can use this formula, which is then also called the transient frequency. Omega sub t is 1 over that tau, and that's over, then 1 over that value will give you again 2 over 15. And that's exactly 0.13333 all the way to, of course, infinity, but that is approximately this value. And this is actually what we see here. So what you actually have is this 2 over 15, or the 1 over this value in the denominator of your expression of the transfer function of the pure integrator, is actually this frequency. And that will give you the unity gain value, and also the frequency that can be read from here, 1 over that value. So that's actually a check we can then use to also see in the Bode diagram that our transfer function is correct. And this is again verified in this form, and that this transfer function is correct. You can also see that why this must be a 1. Let's check that in more detail looking at this. So if I use this formula, or this formula of course, and then substitute in there the unity gain frequency, because that is the unity gain frequency, which is 2 over 15. I just substitute that, so you can see that here, and then moving in that 2 over 15. If I do 15 over 2, j times 2 over 15, this will cancel each other out. You will get 1 over j, because it's just 1. And 1 over j, the value of that one, the magnitude is just 1, and it's 0 dB. Approximately, of course, this is because I wasn't able to get this at exactly 0 dB. So you can see again that this is indeed correct, so that must be 2 over 15 as the frequency where the unity gain is for this system. And that's actually what we have. And again, we have verified that this transfer function is correct, so that's the verification in the Bode diagram. So let's also see that in actual work in MATLAB. So let's jump to MATLAB. So we continue with the MATLAB simulations. This is the real-time MATLAB. What we have is again the script here. We have the system identification example number 6. Again, I have defined a Laplace parameter using this command, and these are the parameters we have determined in our calculations. That was the ki, which is then our integrator gain 4 over 3. And there was a tau I, which is then 10 seconds, of course using that particular time of 10 seconds in our plot. So the model of the pure integrator system was then ki over the tau is. That is then actually what we have, and I can then use the plot to determine the value of this step response. So that's actually what I do down next. So first let me run this script. So I do the run, and you can see that it's running here on the left side on the command window. Then I will check my transfer function h. Let's do that, h, and then enter. Then you will see that this is then our transfer function. This is of course 4 over 3, which is actually the ki, and this is the tau, it's 10, and that is the s. So it's actually what we had. Of course, you can have it also in a different form, which is the 0 pole gain format. Let's also do that. So 0 pole gain format. Then you will have this expression. You can see directly that this is the value, what is actually the 2 over 15. So this is actually approximately 2 over 15, and it is actually the same as this one. So it is actually what you prefer. So let's then look at the step, and of course, since this value, the step input, has an amplitude of 3, you can plot then the RH, which is then R times H. I already prepared that, so I can do that. So I can do the step in RH, and that is what we have here. And I will do also grid on. Then you will have the step response. And you can see here already that at, for example, 10, let me make it larger, and also a little bit larger here and larger there. You can see at 10 I have a value of 4. Let me make it larger. And this will of course go in linear fashion. If you go to 20, which is 10 times, 2 times larger than this one, you will get of course a value which is then 2 times larger than the amplitude, so which is then 8. So it is, as you can see, it is correct for our response. So actually the input is a value of 3, step input, and you can see that this is still increasing without any bond. So that is actually what we have in our step response. So let's also look at the Bode diagram. Then you can only actually you're only interested in the system itself, not in the step height, because that's not really necessary. Again, then the grid on, and you will see what we get. Now I'll make it larger. So what you see is, as we also discussed this in the calculations and after that in the simulations part, you can see that the phase is all minus 90 degrees. That will stay at minus 90 degrees. And you can see that the frequency will go down. And of course, in this case, the frequency is not, the unity gain frequency is not shown. So let me change the limits in this frequency plot. So you can see the unity gain frequency also. So let's look at the limits and let's make it 0.01 for example, and then check for that. And you can see the 0 dB, which is then R1 as a scalar, that will be at for approximately this, which is actually what I had. So of course it's not exactly 0, but it is pretty close. Let's say this is 0. Let's say this is 0, approximately 0, because I had in my analysis also not exactly 0. So this is actually 0, and this was the unity gain frequency. You can also see that. And if I go, for example, 20 dB up, that will make this frequency 10 times smaller. If I go 20 dB down, then this will be 10 times larger. So if I go 10 times larger, it will be 1.33. Let's do that. 1.33, and that's of course minus 20 dB per decade slope. That is a particular characteristic of a first order system, and pure integrator has that. So that is then, as you can see, is minus 20, and I have a frequency of 1.33, which is 10 times this. And again, for completeness, if I make this 10 times smaller frequency, I will have this frequency, and you can see it is now plus 20. So I have 20 dB at this frequency. I increase the frequency 10 times, I get the dB of 0 approximately. And if I go down by, I mean if I increase the frequency again 10 times, so one decade. So what is 1 decade increase? This is a 1 decade increase, and I will again have a reduction of my gain of 20 dB. So you go down by 20 dB, you increase your frequency 10 times, you go down by 20 dB, you increase your frequency 10 times. And as you can see, the phases will be always minus 90 degrees. Doesn't matter which frequency you take, it is always minus 90 degrees. That's actually what we have, and again, the unity gain frequency is exactly as we have discussed. And that's actually the proof in the Bode diagram also, and also with the the step response, that we have the correct model using the given plot for our response. So that was example number 6 about the response of a pure integrator. But of course, different than the previous examples where we have the step response, which settles actually down to a final value. And this is a particular different response. It will be helpful, of course, to also determine the actual response of your controller where you want to find it out if you don't know exactly what is going on the panel. So this might be interesting if you do a step response for that one, and then you can see what the slope is of your response for your PI controller, or maybe the integrator pure as the controller. Okay, thanks again for your attention. That was our example number 6. We will continue, of course, with different examples and different topics. So keep in touch, and if you have any questions or comments, please let me know. Thanks again, and take care, and see you next time.